We're going to finish up now talking about the third aspect that we were going to talk about this week, and that is momentum. Momentum is something called the quantity of motion. It was called the quantity of motion by Newton in the Principia. Momentum is not the same as kinetic energy, and it's important to understand that momentum is not the same as kinetic energy. It's also important to understand, and one of the things I want to point out with these two diagrams is that momentum is a vector quantity, and that means it is different if the momentum is both going in the same direction as shown on the left here, where a large truck bumps into the back of a car, and the effect that that has is very much different than what you have here on the right, where the car ends up on the front of the truck, but in the initial state they were both moving in opposite directions. In one case they have this, in this case you have to overcome all of this momentum and then head it back in this direction, whereas in this case the momentum is actually additive. And it's important to realize that those two situations are different. And in the example problems that I do with this section, I'm going to do an example of each kind. Now, the calculation of linear momentum is quite simple. Momentum, which, given the fact that we just talked about power, it's a little unfortunate, but it is also designated by a P, is equal to the mass of the object times the velocity of the object. So the momentum is equal, as I said, is called the quantity of motion, and another conservation law is called the conservation of momentum. It's conservation with an S, not with a C, and that states that the momentum of an object is constant, that is conserved unless acted upon by an outside force. Another way to think about conservation of momentum is if you take a snapshot at one point in the universe, the total momentum of that snapshot, of that part of the universe that you've decided to take a snapshot of, that is the system, if you will. If you take a snapshot at point 1 and then a snapshot later at point 2, the momentum in those two snapshots for that system has to be the same, even if the situation has changed. And I'll show you what I mean by that when we work some problems. Find the momentum of a 50 kilogram boy running at 6 meters per second. Now, obviously I always start out with a simpler problem, because that's the best way to start out with these sorts of things. And what we have here is a very simple calculation. Momentum is equal to mass times velocity, is equal to, in this case, a 50 kilogram boy running at 6 meters per second. And this one person, the momentum would be 300 kilogram meters per second. And that is the units for momentum, kilogram meters per second. And that's one significant figure here, one significant figure here. Let's take a look at this next one. A 46 gram golf ball is struck by the head of a club, and it flies off at 70 meters per second. If the head of the club has a mass of 250 grams, what is the average velocity of the club head? Assume that the club stops after striking the ball. Okay. So let's look at situation 1 and situation 2. And in situation, we'll assume that these two situations are separated by 2 seconds. We take a picture of situation 1, and we have a club that's traveling and a ball sitting here on a tee. The ball is not moving, and the club is traveling down. And according to this, the mass of the club is 250 grams. We do not know the velocity of the club. The ball is 46 grams and it is currently not moving. And so the momentum of the ball in situation 1 is 0 because it's 46 times 0. The momentum of the club we don't know yet. Now situation 2, we have a club which is now not moving. It still has the same mass of 250 grams. And now we have a ball flying away at 70 meters per second. And the ball has a mass of 46 grams. Now the conservation of momentum would state that the momentum of this situation has to equal the momentum of this situation. So let's write down what the momentum of this situation is. It's 250, which is the mass of the club, times its velocity, which we don't know, plus the mass of the ball, which is 46, times its velocity, which is 0. And situation 2 now is 250, but now the club has stopped, so it's now 0, plus the mass of the ball, which is 46, times 70. And so if we do on this side, we have 250 V, and on this side, we have the mass times the velocity of the ball. The mass times the velocity of the ball is equal to 3,220 kilogram meters per second. And so V is going to simply be this momentum divided by the mass of the club. And if we do that math, the mass of the club has to be 12.88, or since we have two significant figures through here, actually it's only one significant figure here, so it's going to be 10 meters per second to one significant figure. Let's do another problem. And with these two problems, what I want to point out to you is what happens with the fact that momentum is a vector quantity and you have to consider the direction of the momentum. In the case that we just did, the direction of this momentum was from left to right as I've drawn it here, and the direction of this momentum is from left to right. And so there was no change in direction or nothing of that regard. But now with these next two problems, as we look at them, the direction of the momentum is going to become very important. So let's take a look at this first situation. We have a car that has a mass of 1,500 kilograms, and it is traveling at a velocity of 35.0 meters per second. And it runs into the back of a second car, so we'll say this is the first car. It runs into the back of a second car whose mass is 2,500 kilograms, and it is traveling at a speed of 20 meters per second. And that's why he ran into the back, is because the one in front was going slower. Now importantly, it says here they stick together after the collision, and I'll show you why that's important in just a second. And the question is, what is now the velocity of these two cars that are stuck together? So let's do this again. Then we got situation 1, and then say 5 seconds later we have situation 2. And situation 1, we have a car that weighs 1,500, and it's traveling in this direction at 35 meters per second. And we have a second car that's 2,500 kilograms, and it's traveling in this direction at 20 meters per second squared, meters per second. And so that's situation 1. They strike, and now you have a one conglomerate mass of two cars stuck together, and both these cars stuck together are going at some velocity that we don't know. Now, because they're stuck together, we do know that their mass is just the sum of these two numbers, which is 4,000 kilograms. And again, the momentum here has to be equal to the momentum here. And we're going to say that anything going from left to right is positive and anything going from right to left is negative. So the momentum here is this mass times this acceleration velocity, and the momentum here is this mass times this velocity, and that has to equal this mass times this velocity. And this is going to be 1,500 times 35, and it's positive because it's from left to right, plus 2,500 times 20, which is also positive because it's from left to right, and this has to equal 4,000 times this new velocity. So if we do the math here, the total momentum on this side is going to be 102,500 kilogram meters per second, and that's going to equal 4,000 times V3. So V3 is going to be this number for the momentum divided by 4,000. And if you do the math, it's 25.625. And if you look, it's three significant figures, so that's 25.6 meters per second. And you see that it's sort of between the two velocities here, which is what you would expect. That this one would speed up a little bit, this one would slow down, and because this one is heavier, this one's going to speed up less than this one slows down. And so this number makes a lot of sense. Now let's look at the situation, but look at it just a little bit different, because I want to show you what happens when we look at the momentum as a vector quantity. You have the same two cars, but they run into each other head on. So they're not going in the same direction. Now they're going to turn around, and this one's going to be, and all the numbers are the same. We're just going to turn this 2,500 kilogram car around, and they're going to run into each other head on. So if we draw a picture, we've got the first car, and it doesn't change any. It's still 1,500, and it's still 35 meters per second. And it's going from left to right. But now the second car is headed in the opposite direction, so it's headed this way. And it's 2,500 kilograms, going 20 meters per second. And the new situation looks very much the same. It's got two cars now stuck together, and they have some velocity. So now how do we express this difference between this situation and this situation? Well, I said that if it's left to right, it's positive, and if it's right to left, it's negative. So now this one becomes negative. So you have 1,500 times 35 plus 2,500, and now it's a minus 20 instead of a plus 20 because it's going in the opposite direction. Now this left to right and right to left, it's arbitrary, but you have to define it in advance. So now when we do the math here, we're going to get minus 50,000 here, 2,500 times 20. We get positive 52,500 on this side. You put those two together and you get 2,500 total in a positive, and that's going to equal 4,000 times V3. I just brought that down to here. And so now V3 is going to be 0.625 meters per second in the positive direction. 3 significant figures. So look at the difference. Just turning a car around in a different direction changes the answer from 25.6 in the positive direction to 0.625 in the positive direction. Now remember, I told you that this designation was arbitrary, but it's an easy way to think about it because we usually think of left to right being the way we normally do things and right to left being backwards. If this number would have come out negative, then the direction here, by the way, we label the direction here left to right, and we'd label the direction here left to right. If this came out negative, the direction would then be right to left.